Okay, let's start today. So today we'll solve the assignment 7 for the course linear algebra NOC 23 MA 03. Okay, let me share the screen. Okay, so this is the first question. But it is saying that let B be a finite dimensional vector space over R and T be a linear operator on V. Then which of the following options are correct? 4 options are given. So B is a finite dimensional vector space as a T linear operator. So it's saying that T has at least one eigenvalue. So the first option. So T is a linear operator from V to V, where B is a so finite dimension, and let's say let dimension of V to be n, because it's finite dimensional vector space. Then it's saying that T has at least one eigenvalue. What is eigenvalue? Eigenvalue is the your corresponding matrix. Let's call it A. So let A be the corresponding matrix. A be the then let's write it. Corresponding matrix of T. Then eigenvalue of is then determinant of A minus lambda I is 0. The roots of this lambda are so this is a polynomial. So then the roots of so if this equals to 0, then lambda is an eigenvalue of T. Eigenvalue of A or T, right? So this is a polynomial. So note that determinant of A minus lambda I is a polynomial. So if this is a, because we have assumed it's a dimension n, so polynomial of degree n. In the variable of lambda, in lambda, right? In the variable lambda, with respect to the variable lambda, let's write it. To the variable lambda. So this is a polynomial of degree n. So let's call it, so P lambda, we can write it as determinant of A minus lambda. So, and this is, you know, the from the fundamental theorem that it means odd degree polynomial always has a real root. Here it is saying that T has an eigenvalue, means it has to be real, right, for vector space. So if this is a odd degree polynomial, then there must be a eigenvalue, but for even degree there might not be a real eigenvalue, right? So let's take for n equals to 2. For n equals to 2, let's say, so this is even dimension. Consider this matrix A equals to 0, 1, minus 1, 0. So this is called the rotation matrix. It's just rotate the vectors by 90 degree. So then let's, what are the eigenvalues of A? So let's compute this determinant of A minus lambda I equals to 0, means here it is I2. So what will be the eigenvalues? So So minus lambda 1 minus 1 minus lambda. Determinant of this should be 0. So what is this? So determinant, it will be lambda square minus 1 plus 1, right, equals to 0. So which implies lambda plus minus I, right? So eigenvalues are imaginary, right? So it does not have, so which implies A does not have real root. So it is not necessary that the matrix always has a real root. So for odd dimensional, there always exists a real root, at least one, but for even dimension may not be, like for n equals to 2. So the first option is false. T has at least one eigenvalue, it may not be true, right? So this is false. So option number 1 is false. Let's move to the option number 2. What it is saying? Eigenvectors corresponding to distinct eigenvalues are linearly independent. So let's check this. It's saying that eigenvectors corresponding to two distinct values. Let v1 and v2 be two eigenvectors of T corresponding to lambda 1 and lambda 2, where these two are distinct, where lambda 1 not equals to lambda 2. So you have to show that v1 and v2 are linearly independent. So we will show that. We will show v1 and v2 are linearly independent. Okay, so let's prove it by contradiction. So let us assume v1 and v2 are not linearly independent. Let us assume v1 and v2 are. So prove by contradiction. Let's not try this. So we are assuming v1 and v2 are linearly dependent. Means and these two are eigenvector, means they are non-zero. It's so linearly independent, which means that v1 will be c times v2, right, for c non-zero. Means two vectors are linearly independent, then one will be multiple of the other, right? So we know these are the eigenvector, right, of T. So let's apply T. So let's call it 1. Apply T to 1. Then what happened? T of v1, T of cv2, right? So v1 is eigenvector of T with eigenvalue lambda 1. So means this will be lambda 1 v1, and this side c will come up, and so it will be T of v2, which is c of lambda 2 v2, right? So let's call it 2. And now multiply this by lambda, suppose lambda 2. Multiply 1 by lambda 2. What we will get? Lambda 2 v1 equals to c lambda 2 v2, right? So let's call it 3. Now subtract 2 and 3. Then what you will get? Lambda 1 minus lambda 2 of V1 equals to C lambda 2. So this side you will get 0, right? Because these two are both same, so you will get this is 0. And V1 is an eigenvector, so V1 is non-zero, right? Which implies lambda 1 should be lambda 2, right? As V1 is an eigenvector, implies V1 not equals to 0, right? So lambda 1 equals to lambda 2. So which is a contradiction, right? We have assumed, so which is a contradiction. We have assumed lambda 1 not equals to lambda 2, which is a contradiction. So means, so therefore eigenvectors are linearly independent. Therefore V1 and V2 are linearly independent. Right. So option number 2 is true. So option number 2 is correct. So let's check the option number 3. There are infinitely many eigenvectors corresponding to an eigenvalue of t, right? So what is saying? The option number 3, there are infinitely many eigenvectors corresponding to an eigenvalue of t. So option number 3. So let V1 be an, let V be an eigenvector. Let V be an eigenvector of t. Let V be an eigenvector of t. Then note for which implies t with eigenvalue, let's say lambda with eigenvalue lambda, which means t v equals to lambda v. Now what happened to, so then for c not equals to 0, t of cv, what will happen? This, so because t is linear, c will come out and t of v, and this will be c of lambda times v, means lambda of cv, right? So which implies cv also an eigenvector. Cv is also an eigenvector of t, right? Eigenvector. So which implies t has infinitely many eigenvectors, because c non-zero, you can take any number, non-zero number, real number, which implies t has infinitely many eigenvectors, right? So option number 3 is correct. T has infinitely many eigenvectors corresponding to an eigenvalue t. Okay, so this has again cv and again eigenvalue lambda, also eigenvector t corresponding to eigenvalue lambda. To eigenvalue lambda. Corresponding to an eigenvalue, right? So option number 3 is again correct. Now what is option number 4? T can have infinitely many real eigenvalues. So it's saying that T has infinitely many real eigenvalues. So what we have said in the option number 1, that eigenvalues of T are the roots of the polynomial equation, polynomial determinant of A minus lambda I, right? Where where A is the corresponding matrix of T. And this is a polynomial if and as T is a linear map on finite dimensional vector space. So this polynomial has degree n, and let dimension of V equals to n, where T is a map from V to V. Then determinant of A minus lambda is a polynomial in lambda of degree n. So this is an n degree polynomial. So it can have at most n real roots, right? So which imply it can have at most n real root. Which implies that T cannot have infinitely many eigenvectors. So which implies, so therefore sorry, T cannot have infinitely many eigenvalues. So option number 4 is false. T cannot have infinitely many real eigenvalues. So question number 1 is done. Let's move to the question number 2. So okay, what it is saying, a matrix is given. This is a 4 cross 4 matrix. You have to find the smallest eigenvalue of this. So let's find the eigenvalues of this. So means eigenvalues of this are the root of the polynomial determinant A minus lambda, right? So you have to find the determinant of A minus lambda. Here identity is 4 cross 4, right? So this we have to find. So let's check. So what it will be? So it will be determinant of 7 minus lambda 0 0 1 0 5 minus lambda 0 0 1 0 3 minus lambda 0 0 0 0 2 minus lambda, right? Determinants of this matrix should be 0. Now from here you have to find the determinant of this matrix. So you know, in order to find the determinant, just you have to expand it with respect to any rows, right? So let's expand it with respect to this row, 2 minus lambda. Then what will happen if you expand determinant 2 minus lambda, fourth row, determinant will be corresponding to this 7 minus lambda 0 0 0 5 minus lambda 0 1 0 3 minus lambda, and all other entries are 0 for the fourth row, so it will be only one term. Then determinant of this, so this is a lower triangular matrix, and you can show the determinant of lower triangular matrix is the product of the diagonal entries. So it will be 2 minus lambda 7 minus lambda 5 minus lambda and 3 minus lambda equals to 0. So this is a factor, 4 factors, so you get, so lambda will be 2 3 5 7. So these are the 4 roots of this polynomial. So among them, which is the smallest? So 2 is the smallest eigenvalue A. So 2 is the answer, right? So question number 2 is done. And what is question number 3? Oh, so there you have to find the largest eigenvalue. So what is the largest eigenvalue? Here it is 7, right? 7 is the largest and 2 is the smallest. So largest eigenvalue of A is 7. So question number 3 is also done. So let's move to the question number 4. What it is saying, let T be a linear map from R3 to R3, and the map is given for AB belongs to R. B is a vector given. It's saying that it's an eigenvector of T. Then you have to find the value of A. So T is an eigenvalue. So T is a map from R3 to R3. T of x, y, z is x comma x plus y comma x plus y plus z. So, and it's saying that B is an eigenvector of T. Given that B equals to 0, A, 1 is an eigenvector of T, which means eigenvector of T means T of B should be some lambda times B, right? For some lambda, right? So then what will happen? T, what is B? B is 0, A, 1, and this is lambda 0, A, 1. And you know T, action of T over this vector. So what will map? It will map x plus y means 0 plus A is A, and last one x plus y plus z means A plus 1, and this side it is 0, lambda A and lambda. So now equate both sides, so you will get A equals to lambda A and A plus 1 equals to lambda. So from here what you will get? Lambda equals to 1 if A here is non-zero. What happens if A is 0? So if A is non-zero, otherwise let's put it here. So from here what you will get? or you will get, so this, so let's put it here, a into lambda if you put a plus 1 times a, right? So what is this? A equals to a square plus a, or you get a square equals to 0, which implies a is again 0. So you get a equals to 0. So this we have to find the value of a. So what we get? A is 0, right? So the value of a is 0. So this is the answer, value of a is 0. So question number 4 is done. Let's move to the question number 5. In question number 5 it's saying a1 and a2 to n cross n matrix are given with eigenvalues and lambda 1 lambda 2, right? Then we have to check which of the following statements are true. So let's check the option. First option, for C belongs to R, C lambda 1 is an eigenvalue of CA1, right? So what it is given, A, B, suppose let's first let B1 and B2 be the B2 eigenvectors corresponding to the eigenvalues of A1 and A2 corresponding to eigenvalues lambda 1 and lambda 2 respectively. Right. So this is the meaning that A1 B1 equals to lambda 1 B1 and A2 B2 equals to lambda 2 B2, right? Then you have to check that for C belongs to R, C lambda 1 is an eigenvalue of CA1. So what happened to CA1? CA1, so let's apply to it B1. Then what will happen? C A1 of B1. So C, this will be lambda 1 B1, right? So what you will get? C lambda 1 B1, right? So which implies that C lambda 1 is an eigenvalue of CA1, right? So you get that if lambda 1 is an eigenvalue of A1, then C lambda 1 is an eigenvalue of CA1. So the first option is correct, right? So let's move to the next option. It's saying that lambda 1 plus lambda 2 is an eigenvalue of A1 plus A2. So we will show that this is not necessarily true, right? Means this may not hold for general matrices. So okay, right. So we will show so it's saying that lambda 1 plus lambda 2 is an eigenvalue of A1 plus A2 is not necessarily true. Okay, so we'll give a counter example. So let's take this matrix. So let's take A1 equals to 1 0 1 0 1 0 1 0 and A2 equals to 0 minus 1 0 0. So let's find the eigenvalues of A1 and A2. So then what will happen? So determinant of A1 minus lambda equals to 0 means what you will get? Determinant of 1 minus lambda 0, 1 minus lambda is 0. So from here what you will get? You will get lambda into lambda minus 1 equals to 0. So you will get lambda equals to 0 or 1. So 0 and 1 are the eigenvalues of A1, and for A2 determinant of A2 minus lambda equals to 0. So let's check determinant of minus lambda minus 1 0 minus lambda equals to 0, or you will get lambda square equals to 0 means lambdas are 0. So 0 is the eigenvalue, right? So then now let's check the eigenvalues of A1 plus A2. So what will happen? A1 plus A2. So this is 1 0 1 0 plus 0 minus 1 0 0. So what is this? 1 minus 1 1 0. So let's find the eigenvalues of this A1 plus A2. So determinant of A1 plus A2 minus lambda equals to 0, or what will get? 1 minus lambda minus 1 1 minus lambda is 0, or if you solve this, what you will get? Lambda into lambda minus 1 minus 1 equals to 0, or plus 1 you will get, or lambda square minus lambda plus 1 equals to 0. Then solve this. This is quadratic equation. You can solve. The formula is known: minus b plus minus square root of b square minus 4ac by 2a, right? So what are the eigenvalues? So this is 1 plus minus root 3i by 2. So this you will get the eigenvalues of A1 plus A2 are purely imaginary. So from here you can see that you can check that here the eigenvalues 0 and 1 and 0 0. So if you add it, so let's take lambda 1 equals to 0 and lambda 2 equals to here 1. Here lambda 1 is 0 and also lambda 2 is 0. So if you add this, then these are not eigenvalues of A1 and A2. So from here you can easily see that lambda 1 plus lambda 2 is not an eigenvalue of A1 plus A2, right? So this is not necessarily true. So option number 2 is false. But this may be true for diagonal matrices. So note that for diagonal matrices, so this is a note. For diagonal matrices, this statement is true. Mean for diagonal matrix lambda 1 plus lambda 2 is an eigenvalue of a1 plus a2. So this can simply check. Suppose a1 is diagonal matrix, so let's check. Suppose lambda 1 dot lambda n, all other 0, and a2, suppose this is mu1 dot mu n, all other are 0, then what will be a1 plus a2? Then a1 plus a2 will be lambda 1 plus mu1 dot lambda n plus mu1, all other are 0. So here note that lambda 1 and lambda 2 and mu1 and mu2 are eigenvalues of a1 and a2, and there some are eigenvalues of a1 and a2. So here lambda I plus mu1 is an eigenvalue of a1 plus a2, right? So for diagonal matrices, this is true. Okay, let's check the option number 3. What it is saying? Lambda 1 to the power k is an eigenvalue of a1 to the power k. So this is also true. This we can easily verify. So this is option number 3. What it is saying? Lambda 1 to the power k is an eigenvalue of a1 to the power k. So what is a? So a1 to the power k. So let's apply it to b1. So what is a1 to the power k? So this is the composition, right? All a1 this of b, and this is k times. These are all the composition of matrices. So a1 dot. So here it will be a1 b, right? So this will be, so lambda a1 dot a1, here it will be k minus 1 times, and this will be lambda 1 b1, right? So applying lambda a1, then you will get lambda 1 a1 dot a1 b1. Here it is again k minus 1 times. So if you apply like this, do this process, then what you will get? So this we apply, then you will get lambda 1 to the power k times you will do, then you will get b1, right? So lambda 1 to the power k is eigenvalue of a1 to the power k. Which implies lambda 1 to the power k is an eigenvalue of a1 to the power k, right? So option number 3 is correct. Lambda 1 to the power k is an eigenvalue of a1 to the power k. So option number 3 is done. So let's check the option number 4. What it is saying? A1 is not invertible if and only 0 is an eigenvalue L of A1. So L of A1 is the corresponding transformation of A1, linear transformation. So A1 is not invertible if and only 0 is not an eigenvalue of LA1. So this is for option number 4. A1 is not invertible if and only 0 is an eigenvalue of L of A1, right? So we know lambda is an eigenvalue of lambda 1 is an eigenvalue of A1 if and only determinant of AI is not equals to 0, right? AI minus lambda I equals to 0. So this is same as lambda 1 is an eigenvalue of A1 if and only, so this is determinant is non-zero, mean A1 minus lambda is not invertible if and only A1 minus lambda I is not invertible. Right. So now take lambda 1 equals to 0 or put lambda 1 equals to 0. So which will saying that 0 is an eigenvalue of A1 if and only A1 is not invertible, right? A1 is not invertible. So if A1 is not invertible, corresponding linear transformation is not invertible, which implies, so this is 0 is an eigenvalue of A1 if and only L1 of L1 if and only A1 is not invertible, right? So option number 4 is also correct. A1 is not invertible if and only 0 is an eigenvalue of the linear transformation. Now, so this is done. What is option number 5? The product of all eigenvalues of A1 is 0 if and only if determinant of A1 is 0, right? So what is option number 4 is saying? A1 is not invertible if and only if 0 is an eigenvalue. So let's check it. The product of all eigenvalues of A1 is 0 if and only determinant of A1 is 0, right? So, product will be 0 if and only at least 1 will be 0, right? So as we have seen earlier, so by 4 A1 is not invertible means determinant of A1 is 0 if and only 0 is an eigenvalue, right? Of A1. So which is saying that determinant of A1 is 0 if and only product of eigenvalue is 0, right? Product of all eigenvalues of A1 is 0. So product of all eigenvalues of A is 0 if and only if determinant of A1 is 0. So option number 5 is also true. Or you can also note here one thing, that you can actually show that determinant of A1 is product of eigenvalues. So here note one thing. You can show that determinant of A is actually the product of eigenvalues lambda 1 and lambda 2 lambda n. So this is the product of all eigenvalues. Of A. So determinant of A means is the product of all the eigenvalues. Okay, so question number 5 is done. So let's move to the question number 6. What it is saying, let A be a 3 cross 3 matrix with eigenvalues 0, 2, 3, then which of the following statements are true? So a 3 cross 3 matrix is given with eigenvalues D. So means A is diagonalizable. So what it is saying, A be a 3 cross 3 matrix with eigenvalues zero, 2, 3. So A is a 3 cross 3 matrix and it has 3 distinct eigenvalues. So which implies A is diagonalizable. Right? So means which implies A can be written as Q D Q inverse, where Q is invertible. Oh, because we have written Q inverse, so let's do not write this. And where D is a diagonal matrix with eigenvalues 0, 0, 0, 0, 2, 0, 0, 0, 3. Right. So means this is given. A is a diagonalizable matrix where the you can write A is a QD Q inverse, or D is look like this diagonal matrix. Then what it is saying, rank of AI is 3. So let's check the first option. It's saying that rank of AI is 3, A plus I is 3. So first note that we have done earlier, rank of, as Q and Q inverse they are invertible matrices, rank of A is rank of D, right, as Q is invertible. So then what will happen to rank, so let's check what will happen to A plus I. A plus I, this you can write Q D Q inverse, plus you can write Q I Q inverse, right? So this you can take Q, so you can write Q D plus I Q inverse. So where Q is again invertible, because this is same matrix, which implies that rank of A plus I will be same as rank of D plus I, right? But rank of D plus I you can easily check. So what is D plus I? What is D plus I? D plus I will be 0, 0, 0, 0, 2, 0, 0, 0, 3 plus the identity matrix, right? 1, 0, 0, 0, 1, 0, 0, 0, 1, 1. So which is 1, 0, 0, 0, 3, 0, 0, 0, 4, right? So rank of DI is 3 because it has 3 non-zero rows, right? So you can so rank of D plus I is 3. So which implies rank of A plus I is 3. Right. So option number 1 is correct. Rank of A plus I is 3. So option number 1 is correct. What is option number 2? A is similar to diagonal matrix. So what is similar to diagonal matrix? So what is written it here? So let's do it. Option number 2. As A is diagonalizable, which implies A can be written as Q D Q inverse, where D is this diagonal matrix, right? 0 0 2 0 2 0 0 0 3, and this is called the similarity. So this means A is similar to D, right? If A can be written as QD Q inverse with some input where Q is invertible, so which means A is similar to D, right? Which means A is similar to D. And D is diagonal matrix, means A is similar to diagonal matrix. Right. So option number 2 is correct. A is similar to a diagonal matrix. A minus 2i is invertible. So option number 3, it's saying that A minus 2i is invertible. So let's check it. So what will be A minus 2i? As we have done earlier, A can be written as Q D Q inverse, and 2i you can write also Q 2i Q inverse, right? So means this Q D minus 2i Q inverse. So what is D minus 2i? So let's check. D we know 0 0 0 0 2 0 0 0 3 minus what is 2i 2 0 0 0 2 0 0 0 2. So what will be D minus 2i? It will be minus 2 0 0 0 0 0 0 0 1. So D minus 2i, it has a 0 1, so it has rank 2, right? 2 non-zero rows. So rank of D minus 2i is 2, which implies that D minus 2i is not invertible. So which implies also the rank of A minus 2i is also 2, right? The rank of A minus 2i is 2. So which implies that A minus 2i is not invertible, right? Because it does not have full rank. It has map from R3 to R3 and it has rank 2, means A minus 2i is not invertible. So option number 3 is not correct. So A minus 2i is invertible is not true. So this is false. So let's check option number 4. 3 is an eigenvalue of A plus 3i, right? So 3 is an eigenvalue of A plus 3i. So this is similarly you can check. So what is A plus 3i? So this is again you can write Q D Q inverse plus Q 3i Q inverse or Q D plus 3i Q inverse, right? Alright, D plus 3i is, what is D plus 3i? What is D plus 3i? 0, 0, 0, 0, 2, 0, 0, 0, 3, right? Plus 3i, what is 3, 0, 0, 0, 3, 0, 0, 0, 3. So this is 3, 0, 0, 0, 5, 0, 0, 0, 6, right? So we get D plus 3i is a diagonal matrix, so it is, so A plus 3i can be written as Q D plus 3i Q inverse or D plus 3i these, which implies, so these are the, which means 3, 5, 6, 6 are the eigenvalues of A plus 3i, right? So which implies 3 is an eigenvalue of A plus 3i. 3 is an eigenvalues of A plus 3i, right? So option number 4 is again correct. 3 is an eigenvalue of A plus 3i. Okay. So what is the next option? There exists a basis of R3 consisting only eigenvectors of the matrix A. So what it is saying, option number 5, saying that there exists a basis of R3 consisting only of eigenvectors of the matrix A, right? So what we know, so it's saying that R3 means R3 has a basis with where the basis will be the eigenvectors of the matrix A, basis, sorry. So what we know that A has eigenvalue eigenvalue 0, 2, 3. So all three are distinct. So the corresponding, as all three are distinct, so corresponding eigenvectors will be linearly independent. So let's B1, B1, B2, B3 be the corresponding eigenvectors of A. So means A B1 will be 0 times B1, A B2 will be 2 times B2, and A B3 will be 3 times B3, right? And because as 0, 2, 3 are distinct, as 0, 2, 3 all are distinct, so which implies B1, B2, B3, these are linearly independent. and this is an R3, and these are eigenvectors, right? So which implies, so this is linearly independent, and this has 3 vectors, and R3 has dimension 3, which implies v1, v2, v3 is an basis of R3, right? So R3 has the basis with only the eigenvectors of the matrix A, right? So option number 5 is also correct. There is a basis of R3 consisting only of eigenvectors of the matrix A. So option number 5 is also true. So question number 6 is done. Let's move to the question number 7. Okay, what it is saying, let B be a 3 cross 3 real matrix with eigenvalues -1, 0, 1, and U, V, W vectors of R3 be the corresponding eigenvectors, and which of the following statements are true? So given that, what it is given, B, U, this is an eigenvector with eigenvalue -1 times U, right? B is the eigenvector with eigenvalue 0, and BW is an eigenvector with eigenvalue W, right? So then what is the first option? It's saying there exists a vector x in R3 such that LB of x means the corresponding linear transformation take it to U plus B. So note that B has 3 distinct eigenvalues, so B is diagonalizable, right? As B has 3 distinct eigenvalues, therefore B can be written as some Q D Q inverse, where D will be this diagonal matrix, right? -1, 0, 0, 0, 0, 0, 0, 0, 1, right? So note that, so BV, so basically what it is doing, BU it's mapped to -U, BV it's 0, it's mapped to 0 vector, and BW it's mapped to W. So it's like, and all these are linearly independent, right? And these are all, so from here you can easily check that B belongs to the, so from here B belongs to the null space of A, B. This is one observation, and what you can see that U and W belongs to the range space, range of B, right? From here you can see this is one and this is two. These two observations we can see, right? Also U, V and W, these are linearly independent, as these are 3 eigenvectors, 3 eigenvectors corresponding to 3 distinct eigenvalues, linearly independent. As they are eigenvectors corresponding to 3 distinct eigenvalues, right? So it's saying that there is a x in R3 such that it will map to U plus B, right? What is option number 3? 1. Saying that there exists x, so we will show that there does not exist any x in R3 such that LB of x will be u plus b. So we will show this. We show, right? So note. So what we have already saw, u and w is in the range of b. Oh, note what from here what we can show easily. So from star, so from star you can easily check from star. What you can see that nullity of b is 1 and the rank of b is 2, right? And this is from b is from R3 to map, right? B is from map from R3 to R3. So these are the nullity and rank. So if u plus b is, so if LB of x equals to u plus b, so note that, so first note this, u plus b and w is linearly independent, right? Linearly independent. Why? As u b w, right? Linearly independent. So if u plus b is in the range of b, which implies then rank of b will be, rank of b will be 3, right? So which is a contradiction. Means LB of x is u plus b, right? Then rank of this, or this is same as rank of LB is 3. So which is a contradiction. So which implies there does not exist any x in R3 such that LB of x is u plus b, right? So option number 1 is false. There does not exist any R3 such that LB of x equals to u plus b. So let's check the option number 2. The dimension of the null space of LB is 0. So we have checked that from star we can easily check B is in null space. So option number 2, as from star B is in the null space. We can see nullity of B is actually 1. So the nullity of B is not 0. So null space of LB is 1, which is saying that null space of LB is 1. So option number 2 is false. null space of LV is not 0. Dimension of the null space of is not 0, so this is false. Sorry, here you have to write dimension. So option number 2 is again false. So let's check the option number 3. There exist infinitely many x in R3 such that LB of x equals to u plus w. So let's check option number 3. So we'll show this is true. There exist infinitely many x in R3 such that LB of x equals to u plus w. First note that u and w both are in range space. First note u and w both is in the range space of B. Range of B is the, so this is the range of LV, right? And what is B of u? We have seen that this is minus u, and B of w, so this is w. So then what will happen? Then B of, so then what will map? B minus u plus w, where it will map? B of minus u plus B of w, so this will be the u plus w. So it will map this vector to u plus w, right? Now you know that as B is in the null space, means B of B is 0, right? Because B is eigenvector with eigenvalue 0. So you can take this, then you can take B any for any C in real number, B minus u plus C times B plus W. Where it will map? Where it will map? It will map basically B of minus u plus C times B of B plus B of W, right? And B of minus u, you know this is B, B is 0 plus W, so it will map W. And so these are infinitely many vectors, right? So minus u plus CB plus W maps to u plus W under B for any C. So there are infinitely many vectors, right, which will map to u plus W. So option number 3 is also correct. There exist infinitely many vectors which will map to u plus W. Okay, so option number 3 is done. So let's check the option number 4. What it is saying? There exists x in R3 such that LB of x equals to B. So we will show that this is not true. We will show that does not exist any x in R3 such that LB of x equals to B, right? So how to show? So this we have shown earlier, right? As nullity of T B, we know this is 1, right? And what you have to know? The rank of B you have checked 2, U and W already belongs to the range space of B, right? Also U, V, W, we have know these are linearly independent. We have checked this, all these earlier, right? Linearly independent. So if there exists some x, so if there exists x in R3 such that LB of x equals to V, which will imply then V is also in the range space of V, right? So then which will imply the rank of V is 3, so which is a contradiction. Right? So therefore there does not exist, which implies there does not exist any x is not 3 such that LB of x equals to B, right? So option number 4 is false. Okay, so question number 7 is also done. Let's move to the question number 8. Okay, what it is saying, suppose A be a n cross n matrix and diagonal matrix is given and also it is invertible, then which of the following options are necessarily true? Saying that means always true. So A is m cross n matrix and diagonal, right? So A will be look like this, lambda 1 dot 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 lambda n, and all other are 0, right? Only diagonal entries are non-zero. So for diagonal entry, and this is invertible also, given A is invertible. So you can easily check from here that what will be the inverse of this. So first check. So you can check A inverse will be, so because it is invertible given, so you can easily check that A inverse will be lambda inverse dot 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 dot. It will be just inverse of the diagonal entries, right? So this you can check. So what is the first option? It inverse is also diagonal matrix, right? So inverse will be also this, look like this. So option number 2, A inverse is also diagonal. So option number 1 is correct. Rank of A is n, because A is invertible, so rank is n, right? As A is invertible, which implies that A is rank is n, right? Invertible means it's on to, so it has full range. Range is the full space, so means rank is n, right? Which implies A is on to, which implies A has full range. Implies rank of A is n, because A is a n cross n matrix, right? So option number 2 is also correct. Now what is the option number 3? All the diagonal entries of A are non-zero, right? So all the diagonal entries are non-zero. Option number 3. All the diagonal entries are non-zero. So this you can solve easily because A is in invertible and A inverse is given by inverse of this. So if it is 0, 1 by 0 is undefined, so it cannot be invertible. So means all the diagonal entries must be non-zero. Or you can see it otherwise, that as we have seen that, so if some diagonal entries are 0, so if some diagonal entry is 0, which implies what will then say? Then rank of A will not be n also, right? Because it is a diagonal matrix, then rank of A will be less than n, right? As A is diagonal matrix. So which implies A is not invertible, right? And which is a contradiction, right? Because A is invertible given. So which implies all the diagonal entries are non-zero. Or you can use that right? Determinant of A is the product of the diagonal entries, right? Oh, you can also so note that determinant of A, because A is diagonal, you can check that this will be lambda n up to lambda n. So if something is 0, then determinant of A is 0, which means, so if some lambda is 0, which implies determinant of A is 0, which implies A is not invertible. So which is again contradiction, right? So option number 3 means false, or true, means all the diagonal entries are non-zero, right? So let's check the option number 4. Trace of the matrix A is 0. Okay, so let's check option number 4. Trace of the matrix A is 0. So it may not be necessarily true, right? So let's take A to be the identity matrix, right? 1 1 1 1 dot dot dot. So this is the I n cross n. So this is the invertible matrix. A is diagonal, an invertible matrix, right? But the trace of A is non-zero. But trace of A is non-zero, right? So trace of A may be non-zero. So this may not be true always. Sometimes it may happen the trace of A is 0. You might cancel up. Trace of A is the sum of the diagonal entries, not. Trace of A is sum of diagonal entries. So trace of the matrix A is 0. It may not be always true. So this is false. This may not be true. So option number 4 is also done. Now let's check to the option number 5. The matrix A cannot have 0 as its eigenvalue. Right? So this is option number 5. As A is diagonal matrix, so eigenvalues are the diagonal entries, right? So, and we have seen that, as we have seen earlier, that all the diagonal entries of A are non-zero, right? So which implies that all the eigenvalues of A are non-zero. Implies all the eigenvalues of A are non-zero, right? So all the eigenvalues of A are non-zero. So option number, so the matrix cannot have 0 as its eigenvalue, right? So this option is again correct, right? because the determinant of A is the product of these diagonal entries which are the eigenvalues, and this is invertible, means determinant cannot be 0. So all the diagonal entries which are the eigenvalues should be non-zero. So it cannot have the 0 eigenvalues, right? So option number 5 is also done. So so question number 8 is done. Okay, so this completes the assignment 7. Right. So you have completed the assignment 7. Okay, so assignment 7 is over. So okay, let's stop for today. We will meet in the next week. Okay, so let's stop for today. Okay, I am stopping the recording.